So let's have a quick look at the second derivative. So the second derivative, if you were to guess what it is, you're probably going to be right. It is finding the derivative of the derivative. Technically, you could have a third derivative and a fourth derivative, and so on, depending on the function. We are only interested in the second derivative. We'll look at how to apply the second derivative later on. For now, we're just going to look at how to calculate it. But let's start with our notation. If we have a function f of x, let's say, for example, we'll just do a quadratic, 2x squared plus 3x minus 4. Just made that one up. If we were to find the first derivative, the notation would be f dash of x. We know that one already. And if we found the first derivative, that would be 4x plus 3. We're quite good at that now. Now the second derivative is we now find the derivative of that function. So the second derivative, we would say f double dash of x. So this notation is quite intuitive and everyone seems to like it. So if I find the derivative of 4x plus 3, that would be the second derivative of the original function is 4. Theoretically, we don't need to worry about derivatives past the second derivative, but if I did go further to the third derivative, what would that be? 0. And then we couldn't go any further with this particular function. This one would have, that's as many derivatives as we can do. And that will be the case with all polynomials, where at some point you'll get to the point where you can't go any further. But not all functions are like that. For example, this is a pretty obvious one. If I said f of x equals e to the x, what's the derivative of e to the x?
E to the x. E to the x.
So the first derivative would be
E to the x.
e to the x. What's the second derivative going to be? E to the x. And literally you could do that infinitely. The derivative of e to the x, you could go forever. Same with our trigonometric functions. They're not all going to be the same, but they're always, you could continue with our trigonometric functions infinitely amount of times. You go from sine to cos, back to sine. Obviously the signs might be changing depending on which way you're going, but that would have an unlimited amount of derivatives as well.
Does that mean it just swaps the whole time, pretty much?
It kind of does. It doesn't just swap over, there'll be a cycle. We can look at that later on, because the negative sign involved will change it, but there'll be a cycle where it will start repeating. So there's the second derivative, but what about the other notation? Not as nice, I'm afraid. So let's just get a new page. Okay, so if I use this example here, y equals 3x squared minus 6x plus 2. We're going to do exactly the same thing, except the notation's, in my opinion, a bit more confusing. So we already know the differentiation, the notation for the derivative. That would be dy and dx. We've seen that one before. Okay, and in this case that would be 6x minus 6. Now the notation for the second derivative looks like this. D squared y on dx squared. In my opinion, that looks overly confusing.
Can't you do y double dash or f double dash x?
If the original function is using that notation, it's a much preferred way of doing it. But if this is a notation that's presented to you, we really need to stick with that notation. I think it looks overly confusing. We're not actually squaring anything. The squareds in the notation just mean we're doing it twice. We're doing the derivative twice. I'm not going to go into a lot of time now as to how that notation came about. There is a video that Eddie Wu does that explains it quite nicely. I'll link to that in the lesson. But really, we don't need to worry about why it's that notation. We just need to be aware that is the notation for the second derivative. And those squared symbols just mean we're doing the derivative twice. You are not actually squaring any of the items in the function. And so in this case, d squared y over dx squared, 6. Okay. Now, when we're looking at polynomials, we're thinking, oh, this second derivative stuff doesn't look too bad at all. Obviously, it starts to get a lot more gnarly when we start doing the quotient rule, product rule, chain rule, because when you do the derivative of something using the product rule or the quotient rule, it can end up looking like quite a complex function. And then you have to do the quotient rule again. We'll do examples of that later, not right now, but I might just do one chain rule question just for this little sesh. So we will do this one here. And I haven't done it yet, so if I make a careless mistake, please let me know. But this is my original function. I'm going to use the less popular notation. So that's a chain rule question. Let's find the first derivative. dy on dx equals, we're going to have to go 3 times x squared minus 3x squared times by 2x minus 3. All right, so the next step, we now have a product rule question, don't we?
Yeah.
Because we're timesing these two items together. So the next step, to find the second derivative, we're going to have to do the product rule. So you can see that the functions can get quite complex quite quickly. We need to be really careful to watch for those careless mistakes. Let's hope I don't make one now. Wish me luck. So I might just make that a bit smaller. That's not working. Come on. No, that's not. There we go. Oh, that wasn't what I was hoping to do. 2 seconds. I'm still learning the whiteboard. Infinite canvas. Move you out the way a little bit. All right. So we're going to go d squared y over dx squared. Right. So in order to do this, we have to do our good old u's and v's. So u is going to be 3x squared minus 3x squared. U dash is going to be 6 times x squared minus 3x, all to the power of 1. You could expand that out if you wanted to, but I wouldn't recommend it. And now for v, v equals 2x minus 3, v dash equals 2. Okay, let's make a bit more room.
U dash, don't you have to times by the derivative of inside the brackets?
I did. Did I forget to do that? There's my careless mistake. There we go. I was just testing you. Very good. I knew I'd make a careless mistake because I'm videoing this. I always do. All right. So now let's put it all together. Let me just double check I haven't made a careless mistake there, have I? Right. So u dash v, we've got 6. Oh, oops, back to pen mode. 6 times x squared minus 3x times by 2x minus 3 squared. Then we've got plus, if we, because there's 2 of them.
Oh.
Yep. Which, because I made that careless mistake before, I almost didn't do. So thank you for reminding me, whoever that was. Now v dash u, 2 times 3 is 6, and we have 6x squared minus 3x. And we have now found our second derivative.
So you just leave it like that, you don't need to do anything?
At this stage,
So you missed the square. For the u.
where did I miss the squared?
The very end. Last, after you bracket.
Yeah.
I'm missing it.
The U
There it is.
dash, yeah.
Thank you. Just testing again. Well done. At this stage, the question just says find the derivative, find the second derivative, we've done it. If it was a question where we now need to apply that, then yeah, maybe we're going to need, depending on the context of the question, we may need to manipulate it further. Almost certainly you'd be factorising items out of that, I would have thought, if the next step there, because you've obviously got common factors here and here. So you could likely be taking them out, and we'll be looking at the applications later on though. For now, that's all you need to do. Okay,